Hello and welcome to our ICRA 2020 talk on LAMP, Large-Scale Autonomous Mapping and Positioning for Exploration of Perceptually Degraded Subterranean Environments. In this video, we will be presenting our multi-robot SLAM system developed in the context of DARPA Subterranean challenge. Over the past 2 decades, there has been a growing demand for autonomous unmanned exploration of diverse subterranean environments, from tunnels and underground environments to complex cave networks. In perceptually degraded subterranean environments, SLAM is a challenging problem, as sensors must operate in off-nominal conditions. In this work, we present a system architecture to enhance subterranean operation. The contributions of this work are as follows: an accurate lidar-based front end based on scan-to-scan and scan-to-submap matching, a versatile SLAM backend that can incorporate data from multiple sensors and a human operator, an outlier loop closure detection capability, and an extensive evaluation of performance in challenging underground mines across the United States. Here's an overview of LAMP's multi-robot system architecture. The local front end includes a lidar front end that computes odometry estimates and detects loop closures, and a vision front end for detection and localization of objects of interest. The local backend uses post-grab optimization to estimate the trajectory of the robot along with the location of detected objects, and also includes an outlier rejection mechanism to detect and reject spurious loop closures. The result of the local front end and backend is an estimate of the robot trajectory modeled as a sparse set of poses and artifact positions, as well as a downsampled point cloud attached to each robot pose. When within communication range, each robot sends its local pose graph to a base station. The base station fuses the estimates from all robots by searching for potential inter-robot loop closures between the maps, discarding outliers and solving a second PGO problem, this time involving all robot trajectories. A typical 3D lidar, such as the Velodyne Puck Light, generates up to 30,000 points per scan. So there are a large number of noisy or redundant points in each lidar scan that can be removed to improve the scan matching performance and also to reduce the computational load to enable a real-time ego motion estimation. In this work, we decimate 90% of the points in a lidar scan without losing the shape characteristics in the raw point cloud by applying the voxel grid filter to the point cloud, which uses centroid downsampling. We then use the generalized iterative closest point GICP algorithm to perform a scan-to-scan matching, which estimates the relative motion between the point cloud collected at the current time, t+1, and the point cloud collected at time t. Since compact lidars such as Velodyne Puck Light have relatively narrow vertical field of view, the scan-to-scan estimates in narrow underground tunnels are not very accurate. We also use a scan-to-submap matching step, where the latest scan is matched against a local submap. Given the current estimated pose of the robot in the world coordinate system, the incoming downsampled lidar scan is transformed to the world coordinate system. An approximate nearest neighbor search is performed to create a submap by finding the closest points in the map. Similarly to the scan-to-scan matching step, we perform a second point cloud registration to compute the relative 3D motion between the incoming lidar scan and the submap. As we will show in the experiment section, the scan-to-submap matching step improves the accuracy of motion measurements dramatically. The local backend receives the odometric measurements from the front end and periodically instantiates a new key scan, as you can see in this video. In the absence of any prior map of the environment, the accumulation of errors from lidar scan matching can lead to an unbounded drift in the estimated robot trajectory. This drift is inherent to any odometry system and can only be limited and subsequently reduced by detection of loop closures when a robot returns to a previously visited location. In order to find loop closures, we compare the current lidar scan with previously obtained lidar scans. The search for loop closures is performed by constraining the search space to a fixed radius centered at the current estimated robot pose. Here are some examples of the maps obtained in 3 different underground mines without any loop closure detection capability, which shows a significant drift in the estimated robot trajectories. And here are the maps obtained using the loop closure detection capability. The backend includes an incremental consistency maximization ICM module to detect outlying loop closures. In the single robot case, each loop closure can be tested both in terms of pairwise consistency against other loop closures and against the odometry edges. The basic observation is that in the absence of noise, relative pose measurements should compose to the identity along cycles in the graph. Assume that the front end produces a putative loop closure measurement of the relative pose between poses I and J. Then the measurements along the cycle formed by the loop closure and the odometry edges must compose to the identity. If the detected loop closure is an outlier, it will cause the error to be large, and we reject as outliers loop closures inducing average errors larger than a set threshold. Similarly to the odometry check, we check pairwise consistency between pairs of loop closures to check if the detected loop closure is consistent with a previous loop closure. We compute the loop error and build an adjacency matrix keeping track of pairwise consistent loop closures. Finally, by computing the maximum click on the adjacency matrix, loop closures in the maximum click are considered inliers and added to the pose graph. We perform experiments in 6 underground tunnels and mines as listed in the table that are extremely challenging both for perception and mobility. The robots used in our tests are Husky A200 series ground vehicles equipped with VLP-16 puck lidar, an Intel RealSense D435 RGBD camera, and an Intel NUC processor. Using the vision camera on board each robot, objects of interest are detected and the relative position with respect to the robot is estimated. By relying on the ground truth artifact locations provided by DARPA for the Bluestone mines, we obtain a proxy for the ground truth trajectories of our robots by enforcing the ground truth location of the artifacts in the pose graph of each robot and using the resulting optimized trajectory as ground truth. In Bluestone mines, we added the sporadic measurements of the robot poses obtained using a total station to improve the ground truth trajectory. This figure presents a qualitative and quantitative evaluation of the lidar-based front end for both a scan-to-scan and scan-to-submap matching steps in Bluestone mine. While the scan-to-scan matching quickly drifts as it poorly estimates the pitch of the robot due to low vertical resolution of the onboard lidar, the scan-to-submap matching drastically improves the odometry accuracy when compared to the scan-to-scan matching, and in nominal conditions it has a drift of 1% of the distance traveled. This video shows the loop closure detection without the outlier rejection capability in the Eagle mine. As we can see, the map is re-optimized after each loop closure. This avoids the appearance of spurious corridors in the map resulting from the odometry drift. The highlighted point cloud shows matched lidar scans after each loop closure. Including outliers in the PGO typically results in a significant distortion of the entire map. Hence, the rejection is crucial to obtain accurate maps. The map on the left is obtained without outlier rejection capability and is distorted due to inaccurate loop closures. The map on the right is obtained by enabling the outlier rejection capability to remove poor loop closures, and the resulting final map shows no visible distortion. The box plots show the artifact localization error with and without loop closures and outlier rejection capability. This figure demonstrates the multi-robot mapping results obtained at the base station. The map labeled as A shows maps obtained on the base station from 2 ground rovers exploring the Bluestone Safety Research Mine without using any loop closure detection capability. The map labeled as B shows the merged maps on the base station using loop closure detection without outlier rejection capability. Finally, the map labeled as C shows the merged maps with both loop closure detection and outlier rejection capability. In this video, we presented LAMP, a centralized multi-robot SLAM system developed in the context of the DARPA Subterranean challenge, which provides a robust estimate of the trajectories of multiple robots and constructs a point cloud map using 3D LiDAR data. We believe there are several aspects that can be improved, including an improved intra- and inter-robot loop closure detection capability by relying on semantic and geometric features extracted from LiDAR scans, a degeneracy-aware front end to enable detection of degeneracy in an unknown environment, a failure-safe sensor integration for robust and accurate front-end odometry, and a fully distributed back-end post-graph optimization. Thank you for your interest and listening to this talk. If you have any questions, please do not hesitate to reach out to us by email.